She's down there hiding in the corner with her mic off and her camera off.
I'm from the Miami campus, so.
Okay. Patrick, what about you? Got a camera? No. Or Chris?
I'm from the Doherty campus. I'm driving home from clinic. I got like another hour.
Oh wow, okay. Well, you just listen then.
Yeah, that's what I thought I would do. Thank you.
That's cool.
Okay, is my mic on?
Yeah?
Yeah, I'm trying to do the video, but it's not letting me.
All right. Can you see us?
Yes, I can see you.
All right, that's fine. I don't know. So everyone, we have one Miami and the rest is from Atlanta, correct? Because I would know you guys if you guys were from the Altamont because I taught the treatment planning class over there. All right, so with you guys here, what are some of the things that you're struggling with you feel like that you want to go over? We'll make a list.
There are some material that we didn't cover from in the Miami campus.
Okay, from the Miami campus?
So yeah, so for us it was a surprise some of the questions we were asked on our first quiz.
Okay. Like math questions, the equations, or?
Is for example, we didn't cover, for example, for the block equivalent square, we were working with percentages, and now they are working with
like 10% is
exactly.
this and this, yeah.
So that one is like, easy, but I'm pretty sure not all of us have a complete understanding of how to work with them.
I don't make sense of the equation, the percentages either. The way that I understand it for the board questions, they're gonna ask it like you have a treated field of 23 by 10 and a blocked area of 5 by 3. So do you guys know the equation for that?
Not really. I'm currently trying to memorize it from the Laura Nappy calculations book, that iteration, but no.
Yeah, so Laura Nappy is like the Bible she really makes these formulas kind of like into English, I guess you could say. So for the blocked field, and you guys will have to forgive me because this is like my first time using the whiteboard. So for the blocked field, let me find it in her book. But either way, it's basically the square root of the open field. Like you find you do the 12 times 24 and then you minus it by the blocked field. So even if there's 2 or 3 different areas that are blocked, you just minus the blocked fields from each other. Does that make sense? And then hold on, I'm going to give you an example. Please hold. Hey, Celia, I saw you sneak in.
Hi.
How are you?
I'm good. How are you?
I'm good.
They're not talking to
Thank you for doing this review session with us.
No problem. So say the question is, what is the blocked equivalent square for a 12 by 24 cm field with a blocked field measuring 2 by 3 cm, right? So I was just saying, you have to forgive me for the whiteboard thing because it's my first time trying this, but all right, can you see this? Can you guys all see that?
Yes.
Yep.
All right, so basically you're gonna square root this is fun over I'm actually pulling this question from the back of the book. It's number 17 in the Laura Nappy book. So what is the blocked equivalent square for a 12 by 24 cm field with a blocked field of 2 by 3? So you would just put, your 12 here times or by 24. Oh, this is not fun. Sorry, guys. And then you would basically minus it by your blocked field, which was what, 2 by 3 we said?
Yeah, 2 by 3.
All right. So you guys have calculators around, so you guys can help me with the math while I'm suffering over this drawing. So 12 by 24, or 12 times 24 is what?
288. Oh, wait, sorry. 288.
All right, so we got 288. This is like worse than contouring. This is bad. And then minus 2 times 3 is
6.
6. So 288 minus 6 is
282.
so 282. So what is the square root of 282?
16.79.
So your field would be 16.79. That's supposed to be a point. Or if we're gonna look at it like this, it's gonna be 16.8 because the 9, you're gonna round this up. So your new field size is 16.8 by 16.8. That's the effective field size that you're treating. Does that make sense?
Yes.
It's way easier than the percentages, right?
Yes.
Yep.
Yeah.
Yeah. So that's in, I mean, the book, if you go through this Laura Nappy book and you read through it, I mean, it does make a whole lot more sense. I think this is much easier to understand than even the Washington and Lieber. Even that's like, for me, that's hard to understand too. What else do we have besides, where's my eraser? What else do we have besides blocked equivalent square that you guys think that you need extra help with?
The other one was, I think it's very simple, but the magnification factor.
Oh, the mag factor, that's
So,
fun stuff.
I understand the
Let
math.
me add, I'm Patrick. I'm sorry, Diego. I'm Patrick from the Miami campus.
Patrick.
I also struggle with activity.
So activity is like a physics thing. We can go over it.
Thank you.
I also struggle with activities, so did you cover that in physics? Because I don't cover that in my class. Did they ask that on the test that you guys took?
Yes, they did.
Yes.
Yes.
Yeah, there were a few questions related to activity.
Meanies. All right. Well, let's go through Rio activity. So that's 63. Let's go through the mag factor first. All right. So magnification factor, basically you're going to have either the image size over the object size, or you're going to have the source to image over the source to object size. So let's say for a question, so what is the actual size of a fiducial marker in the patient at a distance from the source of 88 cm? So that's image to source, right? When they appear 4 millimeters in width on an image that is taken 120 cm from the source. So first you have to find the factors, right? So the source to image distance is what? What does it say the image is taken at?
120
It says
centimeters.
120 centimeters from the source. So that's your source to image. Okay? And then your source to object, it's telling you is what? Distance. The source to object's distance is what? It was 88 cm. So what is the actual, you want to find what the actual size of these fiducial markers are in a patient at a distance from the source of 88 cm when they appear 4 cm at 120. Okay? So it's telling you your image that is taken at 120. So the image, source to image distance is 120. So that's going to go on top. And your source to object is telling you it's 88. So you're going to put 120 over 88, and it's going to give you a magnification factor of 1.36. Okay. So with this information, you're going to take the actual image size, and the actual image size was 4 millimeters. And basically put your 4 millimeters over the magnification factor, which was 1.36. It's going to give you an object size of 2.9. Do you guys want me to work that out on the whiteboard?
Yes, please.
Yes, please.
Okay. So your formulas are this. It's all about memorizing the formulas. If you guys need to get like a, I don't know what I'm supposed to be picking here. Like even flashcards. I know that some people make their own, what's it called? Quizlet cards, but those formulas, mag factor, gap calc, inverse square, therapeutic ratio, the formulas is what you need to definitely remember. And then the other trick is figuring out what formula do you apply to the question? Like, what does it want? So for a mag factor, you can either have, I'll just show you the thing. I don't know if you guys can see this or not, but you can see right here, it tells you image. Can you guys see that, or is it blurry? Image size over object size, or the image over the object. It's on page 29 of your Laura Nappy book. So if my actual size of fiducial markers, it wants to know what the actual size is, okay? If they're in a patient and the source is 88 cm, love this writing stuff. 88 cm, and that is my source to object. So my formula is, oh, I'm moving it, sorry. SID, which is source to image distance, over source to object distance. You can remember it because I comes before O in the alphabet. Or I'm sure there's other little tricks that you can like come up with. Sit over sod, they say. But basically my image, the actual object it's saying is 120 cm from the source. So basically my equation is going to look like this. I want my object first, so 120 over 88, and somebody do math for me. 120 over 88 is what?
$1.36.
All right, so 1.36. So that's our magnification factor. If it wants to know the magnification factor, that's what it is. But it doesn't want to know that. It's asking what is the actual size of the fiducial marker. Okay? So it's magnified by 1.3 times. So the actual, or the size that we see it is 4 millimeters, or 4.4. I guess it was 4 millimeters. It says in the problem. So you're going to put that over your magnification factor. And so what's 4 divided by 1.36?
2.9.
So the actual size of these fiducial markers are 2.9 millimeters. And if you look at it, it kind of makes sense because the objects are going to appear larger because of the magnification than they actually are. So our objects appear like they're 4 millimeters, but they're really only 2.9 millimeters. Does that make sense? You can do another one. Want to do another one?
Yeah, let's do another one.
Yes.
Okay, fine. Is that Malika here? Or I see the master true beamer? All right.
Yeah.
So, what's that?
Yeah. That's who it is.
Yeah. Okay. So, what is the length of a photon block that is 15 cm from the source when it appears 9 cm in length on the image taken at 130? So, on the image, it looks 130, right? So, that's source to image. So, 130. Remember, sit over sod. And it's saying that 130 from the CM source. So basically it's saying the block that appears 15. So the actual source to image and source to object. So it'd be 130 over 15. The object looks 15, but on the image it looks 30. What's 130 divided by 15?
8.66.
All right, so 8.66, so 8.7, right? So our magnification factor is 8.7. Oh, I lost my, but it wants to know what the actual length of that is, right? So length of a source that appears 9 cm. So our image size is 9. And we're going to put that over because it's magnified by 8.7 times. So 8.9 divided by 8.7 is what? Come on. There it goes.
1.03.
1.0.
1.03. I'm all crooked. So basically it's saying that the object size is really only 1.03 cms, but it appears like it's 9 cm because it's magnified 8.7 times. So basically you're looking at what the image, the source to object distance, it's asking, I mean, when you break apart the word problem, it'll say that appears, like in, for instance, that problem, it's saying when it appears 9 cm in length on an image that is taken 130 cm from the source. That's from the source. That's source to object distance, right? Or source to image distance, I'm sorry, because the image, it looks like it's 100, it looks like it's that big from on the image, right? And the object, it's looking like it's 9 cm at 15 cm, or what is it at 15 cm? So you have to decipher what's source to image and source to object, and it'll usually tell you 130 cm from the image or from the imager. That's your source to image or source to object. Clear as mud?
So I have a question. Do you always divide to find the once you're for this equation, you would divide the 9 divided by 8.7, which is the mag factor.
So,
would you always divide and not multiply?
So if it's asking, if the problem's asking you what is the actual size of the object, you're going to divide what size the object looks like over the mag factor. But if it just wants to know the mag factor, 8.7 is your mag factor. But the question was asking what is the actual size. So you're going to divide it.
Okay, thank you.
Mm-hmm. Activity, I'll be honest with you, I don't teach that, and it's been 20 years since I've looked at it, but we can go over it. Radioactivity, 63. What specific question do you have about activity? 10 cm. So it's saying basically, for example, a radioactive isotope starts with 10 millicuries. What is the activity after 20 days if it has a half-life of 60? So the formula is a fun thing. Activity is basically the AO, which is what it starts with, I believe, the activity where it starts. The T is the days. And then so look at T and 1/2 is the half-life. So for this one, it would be 10 would be where it starts. And it wants to know what it is after 20 days if the half-life is 60 days. So I don't know where it gets this 0.5 from. Let me check. Oh, AO equals the activity times 0.5. So it would be AO, which is 10 times 0.5, and then you take the time, which is 20, divide it by 60 days. Yeah, that's confusing. So 20 over 60 is 0.33. 20 divided by 60 is 0.33. 0.33 times 0.5 is 0.80, and then you would take 10 times 0.80, and it gives you be 8 millicuries. So in 20 days, it would be, instead of 10 millicuries, it would be 8 millicuries. That's really somebody else's ball game. I can figure out this, how to make it sound more, like make more sense and meet with you guys again, but I would have to research this. So I just want to be honest with you, whoever was asking about the activity. I'll do my homework and we'll get back. How about that? Okay.
Thank you.
Hit me with something else that you guys are having struggles with.
I'm kind of having a little bit of difficulty differentiating inverse square law with direct proportions, because the formulas seem to be more or less the same, just without the square root.
Okay,
for the
so
squaring.
Yes, if we can go over direct proportions as well for me.
yep. So inverse square. So anytime a problem asks you what is the intensity or the dose at this distance, or the intensity or dose is blah, blah, blah at this distance. What is it at this distance? If it's talking about intensity, dose, there's all different ways they can use it. But if it's talking about anything measured dose and a distance, it's inverse square. So if it's saying, what is the dose? So the dose is 135 at 80 cm. What is it at 40 cm or whatever? Like it wants inverse square. So for inverse square, basically the dose is inversely proportional to the distance. So the trick for this is don't forget to square it. So do you guys know the formula for inverse square?
Yes.
Yeah.
All right, we got intensity 1.
Mm-hmm.
And intensity means what? Any kind of dose, any kind of anything. Over intensity 2. And then you're gonna have, it flips. Distance 2 over distance 1. And then that part, oh, come on, you gotta be kidding me. this part is squared. Okay? So, for example, if the dose rate, that's an intensity, that's a measurement of dose, right? If the dose rate is 400 millirads at 3 meters from the source, what is the dose rate at 2 meters from the source? So for me, when I read this question, I look at this formula and then I just plug in the spots where it's supposed to be. So the first sentence is if the dose rate is 400 at 3 meters, so that's my intensity 1, 400, right? Everybody follow? At 3 meters, what is the intensity? That's X, we don't know. What is the intensity at 2 meters, right? And that is squared. So you can do this of 2 ways. You can take 2, you can divide it by 3 and then square it, or you can square 2 and square 3 and then divide that. Whatever your math brain tells you to do, because everyone has a different way of doing their math. So if I take my calculator, what's 2 divided by 3?
0.66.
All right, so 0.66 or 0.67, whatever you feel like doing with it. Hold on one second. I think it carries it out like, it's best to carry it out like 3 spots. So for like inverse square. So it would be, let me just move sideways here, 400. This is dysfunctional. I need a pen. I wonder if my stylus works. 400. Hold on, let me try something. 400. Nope, doesn't work. Okay, fine. 400, and then this is point, so this is like 400x. 0.667, right? Because it's 66666 as we like count it 3 ways. So 0.67. And this is the same thing as over 1. For those, like, my math is not my specialty, so this is the way I like to do it. And then you just cross multiply. So 400 times 1 is what? 400. Anything times 1 is the number. So 400 equals x times 0.667 is what?
667.
So you can't times unlike terms, so it's just going to be 0.667x, right? Now what do we have to do to solve for x?
Isolate it.
We got to get x by itself. So it's multiplying. What's the opposite of multiplying?
Divide.
So we're going to divide both parts by 0.667. So there has to be an easier way to draw this. I'm getting good at it though. All right. So our 0.667s over here, they cancel out, right? Anything divided by that is that number. It leaves us with x. And then what's 400 divided by 0.667?
0.60.
What is it?
0.60 or 0.59. Right?
I got 500 and
divided by 0.667.
I got 599.7.
Yeah, I did something wrong somewhere. Please hold. 3 meters. That's that. 667.
599. Okay.
Square this. Oh, we forgot to square it. Ah. See, don't forget to square. So what's 0.667 squared? We'll back up. Hold on. Rewind. So we got 2 See, it happens to the best of us. And that's squared. That's supposed to be a 2. Jeez. Hold on. Let me fix this. Please hold. All right. All right, so 2 over 3, we decided was 0.667, right? And then you have to square it. So what is 0.667 squared?
0.44.
All right.
0.44.
Carry it out 3 spots.
0.445.
445. Oh, this is not fun. All right, which this is ridiculous. Please hold. All right, there it is. So that's going to be over 1. Okay, so now we'll cross multiply. So that is 400. That didn't make sense, right? All right, 400, and this is 0.445x. That cancels out, so it ends up being 400 divided by 0.445. So what's 400 divided by 0.445?
898.
898?
899. Wait, 98.8.
198.87.
All right, so we're gonna go with 900.
That's good.
Round it, okay? So 900 millirads. So let's see if this makes sense. All right, so the question said if the dose rate is 400 at 3 meters from the source, what is the dose rate at 2 meters from the source? So is it gonna be more or less than 400?
It should be more.
Should be more.
Well,
All right.
why?
Because we're getting closer to the source.
Right. So like if you got closer to the sun, you'd be hotter, more burnt. If you got further away, it would be less. So is 900 bigger or smaller than 400?
Bigger.
So then that's correct because 2 meters is closer than 3 meters. And it's inversely proportioned, so it should be about twice what our original was, which is 400. Okay? You want to do another one of those that I don't mess up with? Come on. This is way easier in person, people. Just want to tell you that. All right. Do you guys want to do another inverse?
Yes.
Sure.
All right. Give me numbers. You guys make up a problem. So if the source was whatever at whatever distance, pick a number for how much is our dose?
600.
All right. So if we have 600 at what distance?
11.
11 meters.
Yeah.
All right.
Meters.
All right. What is it at what?
15 meters.
Yeah.
15. So is it going to be bigger or smaller than 600?
Smaller.
Smaller.
All right. Now we're getting somewhere. All right. So we got 15 divided by 11 is what?
1.36.
What is it?
1.36.
1.36. So what is 1.36 squared?
1.85. 86.
1.85? 1.86?
1.85.
Yeah.
All right, we'll go. All right, so we got our 600 over here. And our x, because we haven't figured out what that is. And you know that this whole number can be the same thing over 1 if that helps you add, like keep the place. For me, I have to have a place to times, you know what I mean? Like a placeholder. So 600 times 1 is what?
600.
600. And then 185 times x is
1.85.
All right, 1.85x, because you can't mix x's with numbers because they don't live together. They don't, one's apples and one's oranges, right? Can't multiply like terms. So how do I get my x by itself?
You gotta divide it by 1.85.
1.85, and then I gotta divide the other by the same, right?
Mhm.
So what is 600 divided by 1.85?
322.
What is it? 322?
322.
324.
324.
324.3.
All right, so it's 324 meters, at 324 centigrade, we'll just say at 15 meters, but at 11 meters, it's 600. Does that make sense?
Yes.
Yep. Hi, Raul.
Oh.
You're very dark on your camera there. You're
Oh,
trying
you
to
didn't
hide.
see me? Let me see.
Trying to hide from us. Malik, where are you at? I can't see you.
Ha 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 ha.
No, cameras are mandatory. We said. All right. So the difference between inverse square and direct proportion is one, there's no square, but like direct proportion can go all different ways. So like if you have a field size that is 12 by 15 at 100, what is the field size at 80 cm? That's direct proportion. If you have a dose with a PDD of this, what is the dose with this PDD? That is direct proportion. It's not asking you about intensity, the change in intensity from distance, or the change in distance from intensity. It's asking you about direct proportions. So there's different ways you can set this up. You can set it up field size 1 over SSD 1 equals field size 2 over SSD 2, or you can do field size 1 over field size 2 equals SSD 1 over SSD 2. The whole point is that it's directly proportioned. So whatever you do, field size 1 over SSD 1, that's my favorite just because that's what I've memorized, equals, that's supposed to be equals, by the way, field size 2 over SSD 2. So basically this belongs to this and this belongs to this. Or you can do field size 1, you're gonna get the same answer as long as you keep them where they're supposed to go, equals SSD 1 over SSD 2. That's supposed to be a D, my bad, over SSD 2. So now these belong together and these belong together. Does that make sense? You're keeping them proportioned. You're keeping them the same. So hold on 1 second. Let me go turn on this light over here because I'm going blind. Now I can read. Okay. So if I have a question, so if the field size at isocenter is 12 by 12, what is the field size at 91 SSD if the linear accelerator is calibrated at 100 SAD? So basically it's telling you at isocenter, it's telling you that's SAD, right? Because we know that that's isocenter, correct? So it's telling you it's 12 at 100, 12 cm at 100. So if I want to use this one, I would do 12 because that's my field size 1. I know what it is and I know what the SSD is. That's at 100. Okay? It wants to know what is the field size at, would it say 80? Or any number, but oh, it says at 91. What is it at 91? All you do is cross multiply. So 12 times 91. Do I sound like I'm yelling?
92.
What's that?
No.
1092. That's what I can.
Yes, 1092. So we're going to cross multiply here. So that is 1092. This is funny. And then if I cross multiply this way, I get 100x, right? And you can even put equals. When I need to get x by itself. So I got to divide by 100 on both sides. That cancels out. And I divide by 100. And what's 1092 divided by 100?
10.92.
10.92 or 10.9. So let's think about this. Does this make sense? Due to magnification, due to divergence, okay, if my field size is 12 cm at 100, is it going to be bigger or smaller than 12 at 91?
It's gonna be smaller.
Smaller. Why?
It's closer.
Because you're moving the field size closer to the machine.
Correct, to the source. So because of divergence, it's like a flashlight. If you hold a flashlight up against the wall, you have a little circle. The further you bring it away, your circle gets bigger, right? Your light gets bigger. That's divergence. Same thing happens with the field size. So the direct proportion is basically just, you can set it up both ways. The field size 1 over field or SSD 1 or the other way. If we set it up the other way and we put 12 equals 100 and 91 here, and what is the field size here, or X here and whatever, if you did the math the same way, you would get the same answer. So it's whatever formula you guys like, whichever one you remember. Let's see. I know another one for
Professor Flannery.
Yes, ma'am.
Can I give you another example of the direct proportion that I'm having trouble with?
Yep. Let me use my fancy eraser. Yeah, go ahead.
Okay, it says an entire spine needs treatment with field dimensions of 9 by 45. The 100 cm SAD linear accelerator to be used has a collimator limit of 40 by 40. And the question asks, what treatment distance will be required?
Okay. So it's basically saying there's one like this in the book too. So the linear accelerator is calibrated to 40 by 40, field size 100 SSD. What SSD is needed in order to treat a field size of 180? So basically you got, let me see. Read to me again. 9 by 45 was my lengths. 100 SSD, SAD.
And then it says it has a collimator limit of 40 by 40.
Mm-hmm.
And then what treatment distance will be required?
Okay, let me work it out really fast. Please hold. So it's looking for the SSD. So we know what our field sizes are. So 40 is at 100. Yeah, 40 at 100. And it wants to know what is it? What is the SSD? So 9 at 100. Is it at 40? 40 over 180. So
112.5.
it wants to know what the SSD is because 40 is at 100. That one's very confusing to me because I need to look at it.
Yeah, it is confusing.
So the links are 9 by 45 and it's 100 SAD. And it wants to know what the SSD is.
Mm-hmm.
To treat. So, well, 9's going to be at 100. But they think the only issue is the 45, right? What is the SSD? Read it to me one more time. I'm sorry.
It says an entire spine needs treatment with field dimensions of 9 by 45. The 100 cm SAD linear accelerator to be used has a collimator limit of 40 by 40. What treatment distance will be required?
All right, so 40 at 100, 45 is the X. And I could be wrong with this, but we're gonna go with it. So it's telling you that biggest it can be is 40, but it wants, so F field size 1, we know that 40 is at 100 because that's where it's been the biggest it can be, right? At 100 SAD. It wants to know what the SSD is at, and I'm using the field size 1 over SSD 1, field size 2 over SSD 2. What is it at 40 for 45? As a 9, it'll do 9. What it won't do is 45, right? Because we can't have the 45 because the biggest it can be is 40. So 100 times 45 is what?
4,500.
Oh yeah, told you math is not my friend.
Me neither.
And then we got 40 times X is 40. X, divide that by itself, 40. Jeez, I'm horrible at this. 4,500 divided by 40 is what?
112.5. Yeah, that's
So
what it was.
So your SSD will be 112.5.
Okay. That makes sense.
So, and it doesn't need to know the 9 because the 9 you can do. The problem is the 45 that it can't figure out. So you know,
that's what I was getting
40 is at
confused
100.
I didn't know where to put the 9, so I don't need to worry about that.
But if you did have a problem that said like, okay, your field size is, I don't know, we'll just say 12 by 15 on a film at 120 SSD, what is it at 100 SSD? You're gonna have two different problems. So you know that 12 was at 120. What is it at 100? And that's going to give you what that portion of it is. But you also have to do what is 15 at what it was at 120. What is that at 100? And your new problem will be the answer to both of these. So instead of being 12 by 15, it's going to be at 120. It'll be bigger, it'll be smaller because it's at 100. It's closer. So it'll be, I don't know, I'm just guessing, 8 by 12, we'll just say. I mean, we can do the math if you want to, but does that make sense?
Okay. Yes, I understand.
Okay.
Thank you.
So if you have a problem that has like two different ones, but what it was asking you is what's the extended distance SSD because 40 is as big as it can be.
Okay, got you.
Like if you had a femur that you needed a field size of 50, but the biggest you could do is 20, what SSD would you need to set that patient at? Because at 100, it's 40. Now you got to back that patient up like a TBI. Like you guys have heard of that, right? Like the further away you get, the bigger you can make your field size. So you got to figure out what SSD to use to get a big enough field size.
Okay.
All right. All right. What else we got? You're welcome.
Can we do like the gantry stop angle?
Yeah.
Thank you.
Yeah, the gantry speed or the stop angle?
The stop angle.
All right.
So gantry speed if possible after.
Yep. So we have our gantry dial, right? And different centers have different things. You can have 180 at the top or 180 at the bottom, 0 at the top, 0, 360. 0 is the same thing as 360. So let's pretend we got 180 up here. And 360's down here. Oh, please. 360 is the same thing as 0. Everybody gets that? Okay, so no matter what's at the top or what's at the bottom, 90 will always, always, always be the patient's left. 270 will always, always, always be the patient's, Raul left us. Will always be the patient's right, okay? So if I want to know what the gantry stop angle would be, just say like I wanted to go, started at 270 and I rotated, the gantry was going in a clockwise position, 170 degrees, where would that stop? So it starts here and goes 170 degrees. Well, you know this is 180, right? Parallel opposed. So 170 would be what?
That would
100.
It would be 100 would be your stop angle. Okay. Let me see if I can get some better examples out of there because I'm bad at pulling things out of my head. Do you have a specific problem?
No.
Okay.
I'm free.
Okay. They're all problems, right? All right, gantry speed. Let's see, gantry stop. What is the gantry speed for an arc that moves clockwise, starting at 10 degrees and stopping at 180 and delivers a total dose of 100? So for this example, they use 0 at the top. Oh, that wasn't supposed to happen. So they got 0. Can we all agree that 0 and 360 are the same up here? To me, it helps by writing it. And if you're taking a test, like draw it out, especially like if it confuses you. I'm used to machines with 180 at the top, so 0 confuses me at the top. So if I had, what is the gantry speed for an arc? That was the speed, let's look at the stop angle. So basically it wants to know, to find your gantry speed, you have to have, what's the formula for gantry speed, you guys?
It is.
Without looking.
Oh, degrees.
MUs over degrees?
Yes, degrees over MU. Oh, that makes me proud. You remember. Yep, I can't write an R with this thing, but it's degree, the gantry degrees over MU. I remember it like MU is the first 2 letters of mud, and mud is on the ground. Mud's on the bottom. But you figure out any way that you can. So my problem saying, what is the gantry speed for an arc that moves clockwise, starting at 10 degrees and stopping at 180? It delivers a total of 100 MU. So I don't know my degrees yet, but I do know my MU, right? It's 100. But I have to figure out what my degrees are. So it's basically telling me it's starting at 10 degrees, which is here, and stopping at 180, which is here. Well, I know that from here to here is 180, right? From here all the way around to here is 180. But mine started at 10, which is here. So how many degrees is that?
190.
No.
Nope.
No.
170.
170.
170. If it was 190, it would be here. Yep. It took 10 off because it started at 10, which is here. So that would be 170. So it would be 170 over 100, and that would give you your gantry speed.
So 1.17.
1.7, I believe.
1.7. That's
Sorry,
right.
1.7.
Yeah. So it would be 1.7 degrees over degrees per monitor unit. So basically every monitor unit that machine delivers, it's moving 1.7 degrees. So 1.7, 1 monitor unit, 2 monitor unit, 3, like it's trucking and it's moving fast. So basically, if you're trying to figure out the gantry stop and start angle, for me, the easiest thing is to draw it out like this. And I don't care if you have to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, go all the way around. And then you know that this is 180 from here to here and from here to here. So if you can find a starting place, like say, it started at 15 and it ended at 170. How many is that? How many angles did that go? How many angles? How many degrees?
When you stop?
170.
Sorry.
So it started at 15. So you can do this different ways. You know 360 to 180 is 180, right? You know you take 15 off here. So you can do 180 minus 15 gives you 165, and you know it stopped at 170. So that minus is 10 more. So it went 155 degrees.
Okay.
Yeah.
Okay.
Yes.
So if I was delivering 100 monitor units and my gantry angle or my degrees was 155, it would be 155 over 100. And that would give me how many degrees per monitor units it does. Okay.
1.55.
Sure. Yes. I didn't work out the math, but yes, that sounds right. So let's try this one. There should be like a clear page button. Can I change my color? I'm just kidding. So a clockwise arc therapy treatment will be delivering 130 monitor units. Okay, we know our monitor units. It's 130. Right?
Yes.
All right. The gantry has a speed of 0.9 per monitor unit, 0.9 degrees per monitor unit. If the gantry start is 280 degrees, what will the stop be? So in this case, you're going to change the gantry speed formula to find the degrees. If this is the original formula, we'll need to find the degrees over mu, but according to math principles, if you multiply both sides to get the degrees alone. So instead of dividing, we're going to multiply. Okay, so we're going to multiply our gantry speed, which was 0.9, by the monitor units, and that's going to give us the degrees of how many degrees. So 0.9 times will be 117. So it went 117 degrees.
That's right.
So now you can plug it into your formula. Does that make sense? There's a couple of different ways it explains it. It says now that we know the total degrees, the gantry is rotating, and which direction clockwise the gantry stop angle can be determined. However, this is not as simple as adding 117 by 280. The gantry rotates to the top, so the numbers will increase until it gets to 360. That's because 360 is at the top. This is also known as 0 degrees. Once the gantry gets to that point, the numbers will start over again. So figuring this out requires further calculations, of course. So determine how many degrees the gantry is rotating to get to 0 degrees as mentioned. 0 degrees is 360 and are used interchangeably. So we can subtract the starting angle from 360. So 0 equals 360 minus 280. And the gantry motion is 0 to 80. Now the rotation to get to 0 is known 80 degrees. So from start to over here to here, it took 80 degrees. And now you're going to add from here to here, subtract the 117. So basically remaining gantry motions 37, which is very, very confusing. They have a picture of it on page 62. in the Laura Nappy book that kind of makes a little bit more sense. I don't know if you guys can see that. Basically, it's starting at 280, and then it goes to 0, and then here, but your degrees are going, because it's going clockwise. Does that make sense, Celia?
Yes.
Okay. Got any other questions about the gantry speed? All right, what else we got? Guys know gap count back and forth? Somebody tell me whatchamacallit? Yeah, formula for gap count. Really fast.
Field size over 2.
Field size 1.
Field size 1 over 2. Plus.
Times.
Depth over SSD1.
Yes.
Yep. And then what?
Subtracted
Plus.
by.
Plus.
Okay.
Plus. Girl, you better get your index cards out.
Plus field size 2 over 2 times depth over SSD.
Yeah.
Are you looking at the
SSD2.
No, I don't got the
How
book.
would we know? He doesn't have his camera on.
I don't have the book. I lost my book last semester.
You lost your book and then found it. How are you going to study if you don't have your book, Malik?
I don't really study that much.
Oh, Lord. Here we go. Now he's the study master.
I just really go off the top. I really just go off the top with it.
That is the formula. So when would be an example that you would be using that formula?
When you're doing like a cranial spinal treatment or something.
Yeah.
Yes, a cranial spinal treatment. So what are we trying to determine with the gap count?
We're trying to determine the hot spot. We're trying to avoid the hot spot in the middle.
So avoid the hot spot or a cold spot.
Okay. So we're trying to decide what the gap on the skin is going to be.
Right.
So those two beams intersect at whatever depth the doctor has prescribed. Because if you have them abutting on the patient's skin surface, then there's going to be overlap in the beam because of divergence. Does everybody agree with that?
Yes.
Yeah.
Okay. How many people we have left? Is it just us?
I don't know.
We got 10 participants.
We are here.
Oh, we're 10 of them? Okay. I can only see like 2, 3. Okay. Let's see what else. Oh, I know that one. Hold please. What about dose along the central axis? So somebody work. You guys can work your whiteboard too. You guys have access to this. So somebody else do this one. Okay. Oh, when would the Maynard factor apply?
When it's
Extended
extended.
SSD.
Okay.
Like past
Does anybody know the
SSD.
formula for that?
No.
All right. It's SSD2 plus D max. So depending on what the energy of your machine is. Oh, wait, going back to the gap calc. So the field size and the SSD will be the only thing that changes in that formula. The field size over 2 will always be the same, and the depth will always be the same on both of those problems, whatever is prescribed. Why would you possibly have 2 different SSDs? For those matching fields. So if I had a guy that was face down, prone, and his back went like this, and I had a beam coming from here.
It's because the shape of the body.
Yeah. Because your back's not flat, right? So we're gonna pretend this is his spine, and that's at 5 cm depth. This is our space. but this SSD on this central axis and this SSD could be different, correct?
Yeah.
Because the back is not a straight thing, correct?
Correct.
Okay. Just making sure we all agree on that.
We all agree.
Do you bring us snacks, Malik? Need snacks. All right, so dose along the central axis. Percentage depth dose describes the percentage of the dose absorbed at specified depths along the central axis. So you have this dose A. Yep, this is fun. Dose A over PDD-A. So your problem's going to be like the percentage depth dose at 12, I don't know, centimeters. I'm just pulling something out. Is a certain number. The dose is 250. What is the dose at 13 centimeters when the PDD is another number? So the way you set it up, you guys seen problems like that? Or what is the dose at D max? What is the dose at D max, you guys? Or what is the PDD at D max?
Okay.
1.
Yep. 1 or 100. 100%, or if you're going to make it a decimal, it's 1. So, let me see what's a good. All right. So for a 6 MV beam, the dose at a depth of 6 cm is 200 with a PDD of 0.892. So my dose A is 200. That's what I do know. And my PDD for that was 0.892. Everyone agree with that? It's asking the question of what is the dose at D max. So what is X, the dose at D max. What's my PDD at D max?
100.
Or since this is a decimal, what do we want to make this? 1.0 is the same thing as 100%. Remember, you move the decimal place over. 100% is the same thing as 100.0, right? Well, I'm sorry, the same thing as 1.0. So 100%, we're going to make this percent a decimal. I'm going to take my little decimal point and move it over 2 spots to the one place, okay? That's the same thing. So then all I do is cross multiply. So 200 times 1.0 is 200. And 0.892 times X is
0.892.
892 what?
X.
X. Don't forget that part. We're going to solve for X, get X by itself. I got to divide 892 by both sides. And 200 divided by 8.892 is
224.21.
Mm-hmm.
so 224 point something. Okay, so basically it's saying that the question is the dose at 6 cm is 200. What is the dose at D max? At D max, it's 224. So at 6 cm is 200. Well, what D max is what's the D max of the depth? The D max from 6 MD?
1.5.
1.5. So 1.5 versus 6, it should be more than 200, correct? Because it's closer to the source.
Mm-hmm.
So that's what I think. Always think about your answers. Do they make sense? Plug it back into the problem. Do they make sense? Is it supposed to be, you know, bigger or smaller? Before you even do the problem, think about it in your head. What's the dose at 6 cm is 200. What's the dose at Dmax? Well, Dmax is closer to the source than that 6 cm, so it should be more. Okay? Because now if it was like 190, you'd know you did your math wrong. And a lot of the times with the multiple choice questions that you're going to have on your boards, you can eliminate at least 2 of them in the beginning because they're going to be less than 200. You don't even have to worry about those. Make sense?
Mm-hmm.
Yes.
No, maybe? Okay.
Yes.
What else we got? Think about your test that you guys did with Jessica. And she said you guys did a review test or something. Anybody know what happens to PDD when SSD increases?
Increase.
Okay, just checking, making sure you guys are still there. What else? What else? Tell me what else. We did gap calc. We did blocked equivalent square. What about everybody good on equivalent square?
Yes.
Yes.
What about field weighting? That's my favorite.
Let's do one more of those.
Okay. So your formula is going to be your dose, total dose per day, dose times the weight of the field. I'm going to put WF for weight of the field that you're trying to find over the total of the fields. So if I tell you that this patient is being treated with parallel opposed fields and it's treated, going to be weighted 3 to 1 respectfully, what does that mean?
That it's in that order.
That it is in that order. So APPA. What if I said it was PAAP respectfully? Which one would get the 3?
The first one.
Yeah.
Okay.
Yeah. So read your problem. That's what it's asking. So this patient's going to get 180 a day total. Okay. I want to know what the AP is going to get. So I take my total dose and I times it by the weighted field. What do I want to know? What the AP is getting, right?
So 3.
So that's going to be the 3. And then what's my total of the fields?
4.
4.
And where you get that number from?
By adding 3.
Adding that.
Plus 1.
You add the whole fields. So it would be 3 divided by 4 is
541. 541. That's what.
3 divided by 4 is what?
0.75.
All right. So 0.75 times 180 is
135.
what is it?
135. Let me double check.
135.
135. All right.
Yeah,
So the AP is going to get 135. MU or centigrade, whatever you're trying to figure out, doesn't matter. All right. So what's the PA going to get? And how do I figure that out?
45.
How do you know that?
Because the ratio is 3 to 1.
Yeah.
Yeah, and because the AP is getting 135, so the only thing left of this 180 is 45.
Yep.
Okay. What about if you have 3 fields? What about if you have a 3-field prone pelvis that is going to be treated PA, right lateral, left lateral, respectfully.
PA,
And I
right.
want to know how much the left lateral is getting. What do I do? Oh, they're being treated with 200 a day. Somebody tell me what I do. Anybody. Celia, what do I do?
So we're gonna
You're the
have
only one I can see right now.
we're gonna have 5
What is it?
fields in total.
Uh-huh.
So the complete dose is 200. We divide 200 over 5.
Nope. Dose times the weighted field. I want to know what the right lateral is going to be. This is PA.
Okay. I get what you.
Stop that. PA left. This thing is about to drive me nuts. And right. I want to know what the right's getting. The right's going to